Okay, go for it.
It's on the galvanized nail lab assignment,
Okay.
and it's just about question 10.
You didn't
I'm not. It's
you
the.
want to ask about question 1 and 6 being the same?
Oh wait. Oh, I noticed that, but I didn't. I guess I noticed that, but I must have just ignored it. But yeah, on question 10, I'm just confused with what that's supposed. What I'm
So what I asked you
using.
for 10?
White precipitate is formed when neutralizing the zinc and acid solution with sodium carbonate. Assume sodium carbonate. Assume sodium carbonate even if you used sodium bicarbonate.
Okay, so here, when you react the nail, so I'm going back to the initial steps. Can you see what I'm writing?
Yeah, I can see it.
Okay, so when you react the nail, the zinc on the nail reacts with hydrochloric acid. And you get zinc chloride. And this is aqueous because of the chlorine, the chloride ion. And you get hydrogen gas. So when you watch the video, the bubbling was due to hydrogen gas being formed. So you then take this solution of zinc chloride plus leftover hydrochloric acid, and you add sodium carbonate to it. So this is something you see in the video.
Oh, okay.
Now,
oh,
the sodium carbonate does not react with the zinc chloride, it reacts with the hydrochloric acid. So one of the things that where we make a mistake is that we write down everything that's in the solution and we ask what's going on. The reality is this is what's happening. You get CO2 and you get H2O and you get sodium chloride. And to balance this should be 1, this should be 2, and this should be 1. Okay, so this is what you get. Now in the video, you'll notice that when I add the sodium carbonate to that solution that has zinc chloride and hydrochloric acid, that it bubbles, right?
right.
But I only add in a little bit of sodium carbonate at a time. And each time it bubbles and bubbles. And then finally, when I'm adding a little more in, it bubbles less, right?
Right.
The reason it bubbles less is because you're running out of hydrochloric acid.
Ah.
And that's when you start getting a white precipitate. And then there gets to be a point where I add sodium carbonate and it doesn't bubble. So what does that mean about the amount of sodium carbonate in there? Is it enough? Is it more than enough? Or is it not enough to react with all the hydrochloric acid?
It's not enough, isn't it?
Well,
Or is it?
when it reacts with hydrochloric acid, it bubbles because of the CO2.
Right.
So when I add that last little bit in and it doesn't bubble.
Oh. Is it, you have too much of it?
Yeah, there's too much of it,
There's
right?
too much. Right.
Okay. So that means that now we have sodium chloride in there, right?
Right.
We still have zinc chloride in there because the zinc hasn't gone away, right?
Right.
And we have sodium carbonate in there. Now these are all aqueous. So what's the likelihood that the sodium ends up as part of the solid that forms?
Oh,
What's the solubility rule for sodium compounds?
isn't it the always soluble?
They're always soluble. Okay, so sodium cannot be the cation in the solid, right?
Right.
So what's the only cation available to us for the solid?
Is that
Zinc.
zinc? Yeah.
And it's a 2+ ion. Now, will zinc form a solid with chloride? And here the answer is obviously not because it's soluble. So chloride is not the counter ion. So what's the only counter ion available to us?
Carbonate?
That's right. And if you go back and look at the rules for carbonates, you'll find out that carbonates in general are not soluble. So what is the compound that forms here?
Zinc carbonate?
Right. And it's one of each because it's a 2 and a 2. So if we think about it, what's really happening is the zinc chloride is reacting with the sodium carbonate, making zinc carbonate, which is a solid, plus what's left over here?
Oh, chlorine and sodium, right?
Right. So how do we write the formula for sodium and chloride?
Is it NaCl?
Okay. And how many of these do we have?
Two.
That's right. And so there is the white solid that forms because it happens after the gas forming reaction.
All right.
So that's it.
Oh, okay.
It is this is one of those real world situations where we have a lot of stuff going on, and I'm trying to get you to think about why does this happen at this particular time and not earlier, and what is happening, by the way, that type of thing.
All right.
Okay.
Yeah. I didn't know where to start on that one.
All right. So that was a question. Does anyone else have a question?
I actually had a question. Sorry. I actually had a question on number 9 for the lab assignment.
The galvanized nail?
Yeah.
Okay. Let me, I do have this opened up. I can open that up pretty easily. Calculate the thickness of zinc on the nail in atoms of zinc. Explain any assumptions. Okay. It's actually easier than you might think. So, I'm doing a little fixing here. I got something showing up on my screen that I don't like. Okay. All right. So, here's the nail. This is the iron, and this is the zinc. And I'm looking at a cross section, of course. You can't see this without thinking about cutting through the middle of the nail. Okay. You were supposed to calculate how thick that is. What did you get for an answer?
I ended up getting 0.047 millimeters.
Okay, that sounds about right. Because when you look at the nail, this is about 2 millimeters. And the coating is not really this thick compared to the nail itself. This is exaggerated. The coating is very, very, very thin. And I would have guessed that the coating was at most 0.1 millimeters thick. Because if it's 0.1 millimeters thick, that would mean this would be 2.2 millimeters. And seeing the difference between 2.2 and 2 millimeters would be pretty obvious. It's a 10% difference. But when you look at the two nails side by side, it doesn't look like a 10% difference. So 0.1 is the maximum I would have thought the thickness to be. And you got it to be half of that. So I think that's very appropriate. Okay, so now what I'm going to do is we're going to take a look at this. And here's the iron, and here's the zinc. And what I'm asking you is, How many? How many atoms stacked one on top of another in that 0.047 millimeters of zinc? So before we go any further, do you understand what I'm asking here?
Yeah.
Okay, great. Okay, so what if I gave you something like this? My sister used to work in a shoe store when she was in high school. And being a little brother, I always thought it was cool looking at where she worked. You see all the big boxes of shoes or big stacks of shoes in the back, where you'd bring them out for the customer to try on and so forth and so on. But each shoe box is about 0.5 feet tall. And here I have 3 shoe boxes. So what's the total height here if we were to make a calculation? Well, it would be 0.5 feet per box times 3 boxes, which would be 1.5 feet. So you can follow this very easily, correct?
Yeah.
Now, this is really the height of one box. This is the number of boxes, and this is the total height. Another way to write this is you have the height of one times the number of boxes is equal to the height total, which means that the number of boxes should be the height total divided by the height of one. So this is a very useful equation because it doesn't matter what your object is as long as you know the height of it. So what's the height total that you have for your zinc atoms? I know I'm putting you on the spot, Jackie.
Hold on. I think I have it written down. I just need to find it.
It's actually written on this piece of paper.
Oh, okay. So I thought you made up a value for
Nope.
that. I didn't realize.
It's your
Okay.
value.
So it's in total it's 2.2.
No. It's 0.047 millimeters.
So the total height would be the height of the zinc on the nail,
Right.
not the total.
According to this drawing, isn't that the total height there? The thickness of zinc on the nail?
Yeah.
Okay. Now, what would the height of one zinc atom be? Give it a name. Would the height of a zinc atom be its length, its width? What do we call that?
Yeah.
Now, zinc atoms are what? What sort of a geometric shape?
Circular or
3-dimensional. Circles are 2 dimensions.
Spherical.
What's that? You said spherical?
Spherical.
Excellent. Yeah. So what is the height of a sphere? Try and give it a name.
It would be just its diameter.
Excellent. So we need the diameter of a zinc atom. Now that's something you have to look up. So let's look it up. I'm going to go to my browser and I'm going to type in diameter of a zinc atom. And what pops up here is 2.6 angstroms, which I don't want to deal with because I don't like angstroms. There's this one that says the radius of a zinc atom in picometers. Oh, they actually give in this little section, they actually give the diameter of the zinc atom as 2.6 times 10 to the minus 10 meters. And I've actually heard this, that the diameter of a zinc atom is 260 picometers. That's normally the way you see it. Okay, but nonetheless, they have a 2.6 times 10 to the minus 12 meters. And these actually make sense, and I'll show you why on another sheet of paper. So 260 picometers is 260 times 10 to the minus 12 meters, which is 260 times 10 to the minus 12, 10 times 10 to the minus 2 meters. And if I combine these two together, I get 2.6 times 10 to the minus 10 meters. Okay, so 260 meters is the same as what I'm seeing on my browser. So the number of zinc atoms should be equal to the height total divided by the height of one, which is 0.047 millimeters over 260 picometers. Now this looks like a pretty interesting problem because you have two conversions to do, correct? But let me show you the shortcut. That's the shortcut. It's called substitution. Okay, so you can now see that the units cancel and you divide this number by this number and you get your answer. So go ahead and plug that into your calculator and tell me what you get. I'll do the same and we'll see if we agree.
I got 1.8 times 10 to the fifth.
Okay, so I got the same. You round it to two significant figures because of that. 180,000 atoms. So I want you to think about that for a second. You saw how thick the zinc was on the nail, very, very thin, less than a millimeter. In fact, closer to half of a millimeter. And how many atoms are there stacked one on top of another in that? 180,000 atoms. How many stacks do you think there are on a nail? How many stacks do you think there are on a nail?
Well, would you take 180,000 and then multiply it by the area of the zinc on the nail?
Well, you would actually have to find out how many stacks, you would take the area total and divide it by the area of one atom. And the area of one atom, you would assume that it's 260 picometers by 260 picometers, like that, right? So you could find out how many stacks there are also, and you're going to find out there are a lot of stacks. What did you get for the area total, by the way?
So I ended up getting about 410 millimeters square.
That's about right. Okay. And for the area of one atom, you'd have 260 picometers times 260 picometers. So let's see how many stacks we would have. I've never done this before, and that's why I'm interested. So a millimeter is 10 to the minus 3. So basically we have 410 times 10 to the minus 3 times 10 to the minus 3. So that's 10 to the minus 6. So 410, second EE negative 6 divided by 260, second EE negative 12, and then divided by 260, second EE negative 12. Wow. 6.1 times 10 to the 15 stacks. 10 to the 9, 10 to the 6 is a million. 10 to the 9 is a billion. 10 to the 12 is a trillion. I think 10 to the 15 is called a quadrillion, isn't it? Does anyone know? So we'll just say 6,100 trillion stacks of 180,000 atoms. So what this is supposed to do is give you an appreciation for just how tiny atoms are, that there are 180,000 in a stack, and there's so many stacks. Capiche? We good?
Yes, thank you.
Okay, who's next? You got nothing else? So what do you want to practice? Did you understand I gave you a homework problem that asked you for all of the isomers of C7H16 that have a 5-carbon parent, right? Did y'all get that one? Give me a thumbs up if you got it. Only one thumbs up. Okay, so let's take a look at drawing isomers. And these are going to be alkane isomers. So when you look at alkane isomers, CH4 has only one. C2H6 has two, or one, I'm sorry. C3H8 only has one. And C4H10 has two. So as far as the line drawing goes, there is no line drawing for CH4. There is no line drawing for CH2, but this is the line drawing for C3H8. Now for CH4, here's one of the isomers. Once you draw this isomer, and this has 1, 2, 3, 4 carbons, and if we put the hydrogens in, you'll find out we'll get 10. Once you draw the longest isomer, what you do is you make the parent 1 carbon shorter. So this is 1 carbon shorter, but this only has 3 carbons and we need 4. So we have to add a 4th carbon to it. If we put the 4th carbon here, these are the same. If I put the 4th carbon here, these are all the same. But if I put the 4th carbon there, these are structural isomers. And if you count the number of carbons on this, we have 1, 2, 3, 4. Hydrogens, 3, 6, 9, 10. You find out that these are structural isomers. So the way to find structural isomers with these alkanes is use line drawings, and the number of hydrogens will automatically show up correctly if you have the right number of carbons. Okay, so let's try C5H12. So go ahead and draw for me the longest isomer you can have of C5H12? Once you got it drawn, give me a thumbs up. Okay, excellent. So here, if you drew this, this would be correct. If you drew a W instead, that would be correct. If you drew this, this would be correct. If you drew this, 1, 2, 3, 4, 5, this would be correct. These are all correct. I usually go with what I call the zigzag, and I like to draw mountains. I call these mountains, so I draw mountains. So these are all correct for the longest isomer with C5H12. So I'm going to get rid of these because they're just duplicates. Now the next step is to do this and take that one carbon and add it to this somewhere to see what we get. So I want you to draw all the isomers you can where the longest chain is 4 and there's a branch of a single carbon off of that. When you think you have it, give me a thumbs up. Okay, great. There's this one and there's this one, and these are the same. In fact, if I were to take this guy and draw it in a particular way, so here I've drawn it again. Now, if I were to take it and flip it, you can see it's the same as that. So these are the same. Okay. Are there any others that we can draw where the parent, the longest chain is 4? The answer is no. How about 3? Well, now we have to add 2 carbons to this. We know we can't add them to the ends because if we add them to the ends, we get 4 carbons for the parent. What about this? That's 2 carbons right there. 1, 2. 1, 2, 3, 4, 5. Is this a structural isomer of this guy and this guy? So I'm asking you a question. It's a yes, no. Is this a structural isomer of these 2? And the answer is these are the same. And I'll show you why. 1, 2, 3, 4. That's the longest parent, right? 1, 2, 3, 4. This guy is just this guy like that. Do you see how they're the same? So the answer is this is not a structural isomer. When you're trying to find the parent chain is the one that has the longest number of carbons. So you're not going to let that happen to you again. How about this? Is this a structural isomer of this and this? Look it over and then give me a thumbs up or a thumbs down. For the question is this a structural isomer of the above? So here's what we're going to do. It has 5 carbons, so that's okay. How many hydrogens on this carbon? 3. How many on this one? 3. How many on this one? 3. How many on this one? 3. Why do they all have 3 hydrogens on them? Because the rule is in the line drawing, if there's a carbon atom, and it doesn't have 4 bonds, you add singly bonded hydrogens until you get to 4. How many hydrogens on this middle carbon? Well, it has 1, 2, 3, 4 bonds, so we don't put any hydrogens on it. So does this formula fit C5H12? Does this fit C5H12? 1, 2, 3, 4, 5, 3, 6, 9, 12. So this is an isomer. So what I'm trying to point out to you is that when you're putting the other carbons on these structures, you can put them on together or you can put them on separately. Can I do this? Is this okay? And the answer is no. Why is this not okay? Who wants to venture a guess?
There would be too many hydrogens.
Actually, not. Well, actually, I'm not asking if this is a isomer of this guy. I just want to know, can we do this?
Oh, the carbon in the middle is more bonds. It's
Too
got
many bonds. How many bonds does carbon get to have?
4.
4. No more, no less, just 4. Here it's got 5. So we can't do that. Okay, so we've just done all the isomers of C5H12. Now I'm going to throw you to the wolves, and I want you to do all the isomers of C6H14. Try and draw all of them. There's only like 22, I think. I'm kidding, there's not 22. But go ahead and try and draw all of the isomers of C6H14. Oh, and I've got to apologize to you young people about the world that we older people are leaving you. It's a crazy world. Crazy. We have states suing other states about how they assign electoral votes. I'm sorry. I'm sorry we didn't do a better job for you guys. Okay, when you think you're done, give me a thumbs up. Or when you're at a point where you say, you know, I just don't know anymore, give me a thumbs up. Okay, so I like to do the longest one first. Now, I happen to know that I call this the bird because it looks like a seagull in one of those hotel paintings. I know the bird is 5 carbons. So if I add one little more line, I get 6. And you can double check by touching the ends of each line. 1, 2, 3, 4, 5, 6. So that is the biggest one we can get. And when I say biggest, I mean the longest string of carbons. So what you do is you break it down to only 5 carbons. And we have to put this 1 carbon unit somewhere. This is one place to put it. And this is the other place to put it. We could put it here, but if we did that, these are the same. And one of the ways you can tell they're the same is that when you number the longest chain, you always start at the end closest to a branch. So when you number the parent chain end to end, you always start at the end closest to the branch. So these are the same. You can see that this guy comes off of carbon number 2 in both cases. So is there another fiver that we can draw? And the answer is no. So now we do 4. So now I have 4 carbons. I need to add 2 carbons to it. I like to do it like this. Put them both on the same carbon if I can. Now, what if I put them both here? These are the same. 1, 2, 3, 4. 1, 2, 3, 4. Let's go about naming these. This guy is called pentane. Both of these guys are called, or excuse me, pentane, hexane. So hopefully your eyes were rolling when I wrote pentane here and you were thinking, oh no, he did it again. But I corrected myself. These guys are all called pentane as the parent name. And since the hydrogen here, or this guy here is on 2, this is called a methyl. This is called 2-methyl pentane. This would be called 3-methyl pentane. And either one of these would be called the following, and then we would shorten it. It'd be called 2-methyl butane, because 4 is a butane. Now chemists don't like to do this. So instead we write 2, 2 dimethyl butane. And the reason we do this is because di-2-dimethyl is kind of confusing, right? So we do a 2-2 because one of the methyls is on carbon 2 and the other methyl is on carbon 2. So you might ask the question, why do you have to write both 2's? Well, it turns out there's another isomer. What is the name of this isomer? When you think you have it, give me a thumbs up. So you find the longest chain and you go from there. Now, most of you probably chose this as your longest chain. 1, 2, 3, 4. That's not what I'm going to do. I'm going to choose this one. 1, 2, 3, 4. So this is a 2-methyl. And this is a 3-methyl. And you put it all together and you get 2, 3 dimethyl butane. So you can see that I picked the longest chain. It was probably different than your longest chain, but we still got the same name. So how many isomers do we have so far? 1, 2, 3, 4, 5. And are there any more 4s that we can do? How about this one? What's the name of that guy? When you're done, give me a thumbs up. Okay, if you wrote 2-ethyl butane, it's wrong. If you wrote 3-methyl pentane, it's correct. 1, 2, 3, 4, 5. That makes that a 3-methyl. So I'm hoping that I didn't fool you. Okay, so there aren't any other ways to make an isomer with 4 as the parent. How about 3? Let's try 3. I have to add 3 more carbons to this. 1, 2, 3. Does that work? This is a yes or no question. Is this okay? No. How about this? 1, 2, 3. Is this something that we haven't run into yet? Let's find out by naming it. When you're done naming it, or you're kind of frustrated, either way, or you just want to know, give me the thumbs up. Okay, so I'm going to find the longest chain. 1, 2, 3, 4. So that makes this a butane. This is a 2-methyl. This is a 2-methyl. So you get 2, 2 dimethyl butane, which we already have. So this is not new, and this one's not new. And this ends up being all 5 of the isomers of C6H14. So this is a question. Are you kind of getting the hang of this now? Okay, great. So the problem I gave you was about C7H16. And the question specifically was, draw all of the possible isomers for a 5-carbon parent chain. But we're going to do one better than that. We're going to do all of them. And we're going to try and name them. So I want you to go about trying to draw all the isomers of this guy and name them. I'm going to go ahead and put a pause on the recording because this will take you a little bit of time. Okay, so the longest you can have is this one, 7 carbons in a row, and it's called heptane. Now this is going to be 6 carbons in a row. You could have a methyl here. This is 2-methyl hexane. You could have a methyl here. This would be 3-methyl hexane. I could put a methyl here, but that would end up being 3-methyl hexane also, because you'd count from this direction, 1, 2, 3, instead of this direction, 1, 2, 3, 4. So these are all the hexanes that we can get. And kind of interestingly is if you take a look at the names also add up to 7. Meth means 1 carbon. Hex means 6 carbons. 1 plus 6 are 7. So now we're going to go for the 5s. And there are 5 of them according to me. So here's one of them. Here's another one. Here's another one. Here's another one. And the one that people miss a lot is this one right here. So the names of these are 2,2-dimethyl pentane, 3,3-dimethyl pentane, 2,3-dimethyl pentane, and 2,4-dimethyl pentane. So those are all of the dimethyl pentane possibilities. And then there's this guy, which is called 3-ethyl pentane, because a 2-carbon unit like this is called an ethyl. Okay, so these are all the 5ers. Now we got to try the 4s. So here's 4, and now I need to put 3 more carbons on it. So here's 1, 2, 3, and this ends up being 2,2,3 trimethyl. I've run out of room, so I'm going to write it down here. Butane. We cannot put an ethyl on this guy, because if we put an ethyl on this guy, we end up getting a pentane. So turns out that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 isomers of C7H16. Any questions? Or are we good on that? If we're good, give me a thumbs up. Okay. So for your homework, you were supposed to get these 5. All righty. How about identifying functional groups? Are you guys pretty good at that by now? That's a kind of yes or no question. Or do you want to practice identifying functional groups? So you want to practice. Okay. Did you look at the practice sheets that I posted? They're in the miscellaneous module at the bottom. And what I'm going to do is I'm going to do a new share with you. So here at the very bottom, identifying functional groups practice. You can download these. There is a problem with one of these in that I named the molecule incorrectly. So these are different molecules where you can practice identifying functional groups. The problem here is this one above, this is not vitamin C. You see I have vitamin C down twice. This is actually beta carotene, the bottom one. But what I'll do is go back to the module, and you can practice with these. I have the key right here, the solutions manual, or solutions guide, if you will. So this is the same file, only with me having circled all of the different functional groups. And there are, I believe, 4 pages of this for you to get practice with. So, shall we give this a try? What do you think? Did I lose you guys? Well, we're going to give this a try. So I'm going to go back, and I'm just going to draw some of these molecules, and we'll give it a shot. So let me change my share. I wonder if it's possible to do more than one share. Hold Shift to select multiple windows. Hey, we're going to do share 2 screens and see what it looks like. Okay. Can you, well, I'm not sure what you guys are looking at. Can you guys see my hand here? Wait, I got to pull up my participant list. Can you see my hands? Great. Can you see do you see the PDF file with the different molecules on it. No, huh? So what is this new share? Hold shift for, let me try this again. Now what do you see? Do you see my hands? Okay, well, I guess we're just gonna have to do this. So we're gonna look at my hands, I'll draw the molecule and we'll go from there. Okay, this is a molecule called styrene. It's used to make polystyrene. Go ahead and draw that, identify the functional groups. When you're done, give me a thumbs up. So on the exam, not the quiz, on the exam, I'm going to give you a structure. You're going to have to redraw it and do things like this, aromatic, and this, alkene. On your quiz, I give you things like this. And then it's a multiple choice. So what's the functional group here? Here's your choices. Okay, so what's your functional group? A, B, C, D, or E? When you have a choice, lock it in. And give me a thumbs up when you're ready. Okay, I want you to turn your mics on and give me a drum roll, please.
I did do that.
Come on, I need a drum roll. That's from you three. Give me a drum
I don't
roll.
know if you can hear that at all. Can you even hear this?
Oh, that is just horrible.
Not even sticking up.
It's a ketone. I'm miking you all off. Jeez Louise. Mute, mute, mute. Okay. It's a ketone. And the reason is because you have this carbon double bonded to an oxygen, carbon and carbon. Okay. Here's another one. What is the functional group? Here are your choices, A, B, C, D, E. When you're done, give me a thumbs up. And the answer is aldehyde, because you have a carbon and then you've got that hydrogen there. So I'm asking for a verbal answer. What kind of functional group is that? Who wants to offer their answer? You probably get it wrong. Who's brave enough to be wrong?
An aromatic?
No,
Oh. Wait.
this is an aromatic. Does this have the 3 double bonds in it?
Oh, no.
So this is a cycloalkane. But thank you for being brave enough to be wrong. But that allows us to point out the difference between the two. Capiche? You need to have these 3 double bonds to be aromatic. Okay, so let's try another one here. Aldehyde, ketone, ester, amide, or carboxylic acid. When you're done, give me a thumbs up. Okay, and the answer is carboxylic acid. For carboxylic acid, you need to have that carbon double bond to the oxygen and then an OH. The OH does not have to be to the right. It can be to the left. That's fine. Okay, let's try another one. Okay, there's 2 functional groups here. What are they? Okay, one of them is a ketone, carbon, carbon, carbon with this double bonded oxygen here, and the other is amine. The reason this is not an amide is because you need to have the double bonded oxygen right here on that carbon for it to be an amide. So it's an amine. Amines and amides can be tricky. So what is this functional group? There's your choices. Okay, so hopefully you chose amide. So do you see the difference between these two? The amide, the nitrogen is bonded to that carbon. You need to have that. If the nitrogen is not bonded to that carbon, it's not an amide. All right, that's pretty good practice. Guys have any other questions?
I have is actually pretty simple.
Go ahead.
Basic question. This on the homework, like you draw the isomer for the nitrogen in the middle and have 3 bonds to carbon.
Oh, draw a structural isomer for this guy?
Yeah. Okay.
Okay, so yesterday I said this is a structural isomer. That's one of them. But now that I gave everyone this one, you have to come up with something different. So this is 3 carbons, 9 hydrogens, and 1 nitrogen.
Yeah.
And if you draw this one out, this is CH3, NH, CH2, CH3. And if you count the hydrogens here, 3 plus 3 plus 3 more is 9. So when I took this guy off of the nitrogen, I had to put a hydrogen there. And I basically took this guy off and put it right there. Are you with me?
Yeah, yeah.
Okay, so what else could I do here? Can you take that off and put it somewhere?
Put it continuously for the other side.
Like that, right?
Yeah.
Okay,
That's
but
what I'm saying there.
let's see how many carbons do we have?
3.
Good. How many hydrogens here?
3,
How many here?
2,
How many here?
2.
So 3, 2, and 2 is 7. We need 9. Where are the other 2 hydrogens?
Oh, in nitrogen?
Right, because nitrogen has
Oh,
to have
okay.
3 bonds, right?
Yeah.
So this is one. There's one more that you could have done, and it's this. Instead of continuing, you could have done that.
Oh,
Let's count how many hydrogens here. How many hydrogens there?
3,
Good. How many there?
3.
How many there?
1.
So that's 7 also, right?
Yeah.
So really, you'd have that. But you could just write this.
Oh.
So these are all structural isomers of one another. Whoops. These are all isomers of one another. Okay, on?
Yeah.
Okie doke.
Oh, and just a little bit more about
Sure.
the functional group of that one.
Oh, it's an amine.
I mean,
For an amine, you need to have a carbon bonded to a nitrogen.
yeah. Oh.
So here's the
I
carbon.
I thought we have to have oxygen with it, so like have
No,
double
that's
bond oxygen.
amide.
Oh, never mind.
Amide is
Yeah.
you have to have the oxygen. So they're different.
Yeah.
Some people take a look at this and they say, oh, this is amide and amine. No. If you have the double bonded oxygen, it's not an amine.
Okay.
Okay?
Yeah.
So it's one or the other, not both. Anything else, folks? All right, next week is finals week. I'm gonna go ahead and Zoom on Monday and Wednesday. Your fourth exam will be Tuesday. Your final exam will be Wednesday. For the fourth exam, you get a 3x5 card as usual. For the final exam, you get an 8.5 by 11 sheet of paper with notes that you get to bring into the exam. And I will still post a little periodic table in the instructions. Any questions about that? So I'll say it again. Well, Harry, you're saying no questions. I get it. Harry's just answering the question I asked. So I'm going to reiterate. Tuesday is exam 4. It will be over valence bond theory, molecular orbital theory, gases, and more recently carbon. You get a 3-inch by 5-inch card, front and back. You'll upload files and so forth and so on. For your final exam, it's going to be 55 questions, multiple choice. There will be no file uploads. You get to use an 8.5 by 11 sheet of paper. And I will give you a periodic table, but I'm not going to give you anything else. So I don't plan on giving you constants like R. I don't plan on giving you formulas like E is equal to negative RHC over N squared. So you want to be careful about what you write on that 8.5 by 11 sheet of paper. And also, I will tell you this, for the final exam, you want to focus on the things that you think are the major parts of the class. I don't tend to put things on there that, or too many things on there that are niche ideas. We're like, oh, you know, we talked about that, but not in great deal. Like, for instance, there was a question I asked about on your homework about ozone and molecular orbital theory. And I didn't talk about that at all in lecture, but it's in your book. So if I were a betting person, I would bet that there's nothing going to be on the final exam about ozone and molecular orbital theory. But on the other hand, you know, maybe there might be a question about the different parts of molecular orbital theory on the final exam. You know, the question says, all of the following are parts of molecular orbital theory except, you know, so things like that. And with 55 questions and a 2-hour exam, you have to understand that I know that you get 2 minutes per question. So some of the questions should take you 10 seconds, some 5 minutes. On average, they will take you less than 2 minutes. And you should probably finish with the final exam in an hour to an hour and a half and have an extra half hour to hour to look over your answers. Second thing I'm going to say about the final exam is this, is since it's multiple choice, there are definite guidelines for how to take the multiple choice test. Normally in a face-to-face setting, you never skip a question, because if you have a sheet of paper and you skip a question, like you skip question 13, unlucky 13, you go to 14, you write the answer for 14 and 13, for 15 and 14. By the time you get to question number 23, you finally figured out that, oh, I'm putting the answer down in the wrong place, and you've messed up big time. In a virtual multiple choice, you get to go back to the questions. So what I would say is don't skip, because you can go back and change your answer. Pick an answer. If you don't pick an answer, you got it wrong. If you pick an answer and you have no idea whether you're right or wrong, you're going to get a 1 in 5 correct. So pick an answer. But on a sheet of paper, write down, go back to problem number 23 or something like that. So answer each problem, and answer each problem with your gut instinct. And when I say gut instinct, I don't mean like just look at the answer and go, oh, I like that one. What I mean is make sense of the problem, come up with an answer in your head, and if you see that answer as one of the multiple choices, pick it. It's probably right. It usually works that way. And if you're unsure, you go back to it later. So pick your first answer that you come up with your head if you see it on the answer sheet. If you don't see this answer on the answer sheet, then you need to work it out and pick the correct answer. Capiche? And the last thing I'll say about that multiple choice is this. If you have picked your best answer, eliminated stupid answers and picked your best, when you go back to that, you never change it unless you're absolutely certain that you are changing it to the right answer. Because it's been shown that people that do that, they will pick the correct answer sometimes, but they will more often than not change a correct answer to a wrong one. So the other thing I'll say for the multiple choice test is make sure you time yourself. If there's 55 questions and you're on question 27 at the hour mark, you're doing okay. You might want to speed things up a bit. But your goal usually when you're doing a multiple choice test is if there's 55 questions and you have 2 hours, you want to be at least on question 30 or 35 or 40 at the hour mark with only 15 left or 20 left. You want the bulk of it done in the first hour so that you can finish the rest and then go back and review the things that you needed to review. So does everyone understand the multiple choice strategy? Okay, now, have your teachers ever told you about the multiple choice strategy before? Why not? Have you ever had multiple choice before? Okay. Now, the other thing I'm going to say is this. Sometimes students say, if you don't know the answer, pick C. That is not a good strategy. Because teachers know that one. So chances are the answer will not be C. Because teachers love to mess with students. All right. Actually, for my multiple choice, I have this little thing where it says shuffle the answers. And they just get shuffled automatically. So I don't know whether the answer is C, D, or E. I just know that I picked the correct answer, and when it gets shuffled, it's still the correct answer. Capiche? We good? Okay, hope to see you Monday, and I hope to have everything graded by then too. I've been trying this little experiment to see if I don't grade them, will they grade themselves? And I found out they don't. All right.
Oh, I have a question. Like, was the paper like how big the paper? It's just like the paper of the notebook, or like
8.5 by 11.
Just print the paper, right?
Yeah, for the exam.
Okay.
Oh, so
Yeah.
I did the little
I use
chart
printing
thing that we
paper.
did together,
Mm-hmm.
and then
You could use
yeah,
you could use notebook paper too.
Okay.
it's like
Yeah.
one of those. Here, let me screen share.
You could also use graphing paper, because graphing paper, sometimes those little lines help you to write really small. Know what I'm talking about?
Yeah.
So it's up to you. All right. Hopefully I'll see you Monday at noon. Toodles.
Hey,
So it was like this.
Bye,
It was
guys.
like this was
Bye, guys.
Bye, everyone.
Bye.
hey.
and then I click this.